Hey, good morning, everyone. Thank you for joining. So we'll get started. The future of biomanufacturing is now, and latest advances in downstream processing. So rather than start with bottlenecks in downstream processing, I figured we'd morph it a little bit and talk about the advances, of course, that address bottlenecks in downstream processing. So just a little bit about what we are going to cover today. Who is Sepragen? What are the challenges in downstream processing? And so we'll discuss a little bit about these challenges that the industry faces, and then innovative approaches that can be taken to address these challenges that certainly Sepragen is involved with, and some of the solutions that are part of this approach to dealing with these downstream challenges. Well-known radial flow chromatography technology, single-use chromatography systems, inline buffer dilution systems, and now we are launching a continuous purification platform with integrated buffer blending. Incidentally, we are the only company in the world that does this. People might do continuous purification, they might do buffer blending, but they certainly have not concatenated and integrated these processes into a single scale. So first, who is Sepragen? We've been in business for well over 25 years. The company owns 16 patents, and we are filing new ones. And our products are today used to make 24 commercially approved biologics. So these are not, for people who are not familiar with this, these are not, or have they been used in GMP production? Has somebody used it in pilot plant? The answer to that is yes, yes, yes. And they have been scaled up all the way into commercial manufacturing. And these drugs, biologics, have been produced for the last couple of decades with all the scale-up issues and everything else. And today there are over 200 global installations. And currently these biologics, the value of these biologics exceeds 10 billion. And so the company provides technology, of course, for radial flow chromatography, which we'll discuss in a minute. We have automated systems, chromatography systems, benchtop systems, large-scale customized systems. We also provide single-use purification systems. So in multi-product facilities, this is very useful. The whole flow path can be removed and new ones installed so that there's no cleaning validation required. There's no cross-contamination from one product or one batch to the next. And then, of course, we pre-pack these columns with resins of your choice. Many times people use them for single use because they don't want to have to deal with cleaning validations. But many times they also reuse, but they like the convenience of it being pre-packed and certified from the factory. Quantacep buffer dilution systems and buffer blending. Well, buffer management is a big problem. And so the ability to use concentrated buffers and simply connecting to a water for injection source at the facility and use it as a dual diluent then allows you the ability to use much smaller tanks, not have big tanks. So even though titers might be going up and scaling up, you can still continue to do your purification in a small space. And buffer blending, of course, takes it to the next level, which is you don't actually have to make buffers. You take stock solutions. So if you wanted to make a buffer like sodium phosphate, 0.05 molar sodium phosphate, pH 6.9, then what the buffer blending system has the ability to do is it takes the concentrates of the two buffer constituents, which might be monosodium phosphate and disodium phosphate, and blend them together and then dilute with water. And the blending ratio then not only defines the concentration of the phosphate, but also its pH. And then you can add salt so that you can use then that same buffer for elution. And last but not least, continuous downstream process. Everyone's interested in higher productivity. Rather than make large batch system for processing large volumes, it's far more effective to have an assembly line where the product is continuously being generated 24/7. So if people have upstream perfusion bioreactors, then the ability to integrate downstream skids to such a perfusion system upstream would give people the ability to do continuous processing, and thereby, instead of having, 10 or 5,000, 10,000 liter bioreactors, you could do something in 1,000 liters or 2,000 liters. And our products have been used across the spectrum of users in the industry, some in clinical production, some in commercial production, and we have examples of uses by these people of our equipment in various GMP manufacturing environments. So on the left here, you see radial flow chromatography columns. This is an installation where they are doing between 10 and 15,000 liters of biologics purification. So in this case, it happens to be human plasma, and they're fractionating immunoglobulins. Those stainless steel vessels that you see in the front are not tanks. They actually are radial flow columns, 350 liter size, 4 of them running in parallel, processing huge quantities of biologics, multiples of tens of kilograms of protein per day. Okay, and then what you see here is the Quantisep is one of our bench scale chromatography systems. We have many. We have a whole line of systems going from the bench scale, just as you might be used to, other well-known vendors in the space. Well, we are not too far behind. We have some very, very unique and cool products that give you more bang for your money. What does that mean? That means in the same footprint and the same dollar, you're able to do a lot more. This is an example. The middle system that you see here is an example of this. This is a Quantisep LX system, the only kind of its kind in the world. And it's a double-decker system, so it's 2 systems in one. And on the top level, you have small valves, small pumps, and another set of valves here. So the pumps can run between 0 and 100 mils a minute. Okay, so you can use it. And on this side, so the flow comes from the left, goes through the pumps, through the sensors, and comes out. The fractions come out in the front, and the columns are to the side. So you can run between 0 and 100 ml per minute. And if you choose a different flow rate, and if you wanted to scale that same process up, or different process up to, let's say, 0 to a liter a minute, so you wanted to run it on a 5-liter column, let's say, that particular process, well, you don't have to go anywhere. Simply do it on the same machine. And you set your flow rate range to 0 to 1 liter a minute. We have 2 pumps at the second level, so at the level below. So this is like a double-decker bus. So on the lower level, you have 2 pumps, and their flow range is for gradient capability. So each pump's flow rate range is 0 to 1 liter a minute. And you can see you have 10 fractions in the front. You actually have the ability to run 3 columns. So these are mini sanitary connections that go to the columns, come back from the column, and the fractions come out in the front. And you have buffer inlets on the left-hand side. So then you can do pilot scale runs, GMP runs in the same facility, with the same equipment. So you essentially get 2 for the price of 1. Very, very popular model. And the next machine on the left-hand side, we are the only company again in the world that provides this kind of machine. It's a single-use disposable flow path system, which is bench scale. Nobody has a single-use bench scale system with removable flow path. So here again, you can, this is a Quantisep 3000 system, 3000 SU, and in this you can have 3 flow paths, so 3.2 millimeter flow path, a 6.4 millimeter flow path, and a 9.6 millimeter flow path, and they give you the ability to make your separations in different flow rate ranges, 0 to 300 mils a minute, 0 to 1.5 liters a minute, and 0 to 3 liters a minute. And then we have high flow skids. So this is the 10 liter a minute system here, which is a little bigger than a dishwasher. Here is a system with integrated buffer dilution. So in this case, instead of making 1x buffers, you can make 10x buffers. You can program your chromatography run, and you can connect one of these inlets to Wi-Fi or to water, and then you can make concentrated buffers, and then the system will make the 1x buffer for you and do the chromatography and everything. So you don't have to do any of that. All that mixing is done online, and the chromatography parameters are programmed in. Okay, and the last picture that you see is the dual continuous capture system, particularly with antibodies. When you're coming through your harvest, let's say a perfusion, 2,000-liter perfusion bioreactor, you can load the raw material directly onto the column, to one column, and when one is saturated, the machine would flip you to the next column where it would continue loading. All the first column is going through the wash, elution, regen, and equilibration. And what you see here, down here, are buffer inlets. So you can have concentrated buffers and buffer components. So there's a phosphate buffer, monobasic, dibasic phosphate, salt, and water. And with that combination of four, you can make pretty much any buffer you want. Okay, so if it was an acetate buffer system, you'd have the acetate salts, citrate salts, or whatever. Okay? So what are the challenges with downstream processing? Well, with antibody manufacture, there's a typical kind of diagram showing a typical antibody manufacturing process where you have your seed train and scaling up of the bioreactor, your buffer prep, going through protein A capture, viral inactivation, cation exchange, anion exchange, and through virus filter, dye filtration. Sometimes now you're using nanofiltration, and then through the point two to fill and release. So while the upstream process, everyone is using subs and other kind of disposable bioreactors, the downstream process has been a little bit kludgy, and people have usually tended to do that in a batch mode. Well, with Sepragen's technology, you can now do it continuously. But here's the thing, that over the last decade, with antibody manufacturing, as with anything else, the cell line development people have done a phenomenal job, and the upstream guys have done a phenomenal job. So the titers in these processes have become very high, and they keep increasing. What that means is that the downstream folks have to keep pace with that increase in titers, and that has become a bottleneck and a nightmare, frankly, because once the titers go up, sizes of the columns have to go up, the sizes of the skits have to go up, buffer volumes have to go up. So here it is. This is what downstream groups are besieged with, where you have the need for larger columns as titers are going up, more columns, more cycles, bigger skids, longer campaigns, more headcount, more documentation, more training, more infrastructure, more testing, more QC. And all this means more time and more dollars. And that's just the direct process. And of course, the indirect problem with that is that you have to increase your buffer making capacity. You have to have a larger square footage of plant. You have to have more people. You have to have more Wi-Fi capacity. So infrastructure support, air handling system, electrical capacity, equipment cleaning, waste handling, production planning, multiple shifts. So there's lots of consequences. Used to be you just increase the titers upstream, everything would be good. But now that's not the case. And especially in facilities that have already been built out, retrofitting these facilities becomes, and the square footage becomes very expensive. It affects your time to market. Remember, we talked about how we can help time to market. So the best thing is, if titers are increasing upstream, how can you use the same facility and the same infrastructure, but do more? And I think some of the things that we are talking about here will certainly enable you to do that. So whether it's radial flow columns have been around and sometimes actually overlooked. People think, well, they've been around, yeah, but I use axial flow. A lot of times process development is done in development labs where people just take little high trap columns for process development, where they don't see issues of scale up, where they don't see issues of pressure, and they simply develop a process, toss it over the fence, and then the guys at MSAT manufacturing have to deal with the consequences of scale up, which is where the issues show up. So if you have conventional columns, which are very big, make these columns, not tall columns, they're wide columns with adjusters. We have customers routinely who are at 1 or 2 meter scales, and have problems packing these columns, running these columns, cleaning these columns, unpacking them. And often, with the increased bed height that these columns use, then you have problems of pressure. And so the use of radial flow columns, it's a very unique geometry that works extremely well with ion exchange, affinity, hydrophobic interaction chromatography, and allows you to increase the throughput significantly and reduce your cycle time. So any time that you've lost as a consequence of increasing titers can be gained back simply because you can speed up your chromatography by that amount. Since the footprints of the column are very small, you usually use the columns in the same facility. Of course, higher flow resins is another way to go to use smaller columns. And then the last thing, of course, that people are looking at is continuous processing, because if you're continuously processing as opposed to doing one large batch, a day, then if you're doing multiple cycles continuously, then you can use much smaller columns, and your footprint of the plant can be reduced significantly. So here are examples on the left of the columns, and you can see our system here with much smaller footprint compared with these older systems which take up a lot of room. Here's the Qantas F1000 LF system that we talked about, where you have the ability, you can see two pumps here on one level and two more pumps. These are the lower flow pumps, and these are the higher flow pumps with higher flow valves. So in the same machine, you're able to do both PD and scale-up work. It gives a user a lot of flexibility. So the titers are going up, or they need to make larger batches to get to and do some preclinical studies, animal studies. They don't have to wait for time in a pilot plant and get in queue so that they can make material. With the same machine, they can turn on the high flow mode and make material and get those development and scale-up runs, engineering runs, preclinical runs, animal runs done faster with significantly less capital investment. If you're looking at disposable resins, because you don't want to go into cleaning validation, we certainly have low-cost ion exchange resin options, and we can certainly pre-pack columns for you, so you don't have to have that as part of your work process. The columns will come ready to plug in and use, and that way you can reduce cycle times and you can increase the efficiency of turnaround time per batch in your process. And then, of course, single-use systems. These are very, very useful. Many of our clients are using these machines where you can simply remove the entire flow path, which comes with pinch valves, UV conductivity sensors, pressure sensors, air sensors, all of which are integrated into the flow path and removable, and the entire flow path can be removed and exchanged in 15 minutes. And of course, so we start with radial flow chromatography, and the real advantage of radial flow chromatography is faster separations at lower cost and very small footprints. I mean, the footprint of a plant this size with conventional columns would be 3 times as big or 4 times as big. And all our columns are flow packs. You don't have to have big packing systems and adjustment of heads, hydraulics moving up and down to pack these columns. You can simply make a slurry and pump it in and pack the columns. So you can typically get about 4 times the flow rate, much better resin usage. The columns are much smaller, of course. The back pressures are much smaller. The footprints are much smaller. And also, because you can go much faster, in clinical production, these columns can be very useful in reducing the cost of protein A. Because let's assume you have a run that takes 8 hours. If you can do that run in 2 hours, which we have enabled, which radial flow columns enable, then you can use a column which is 1/4 the size and simply do 4 cycles, 2-hour cycles. Instead of 1 long 8-hour cycles, they do 4 short 2-hour cycles, and the same amount of time, then they can make the same amount of, purify the same amount of product, except with a column which is 1/4 the size. And so in our experience, people have cut down the capital cost for that particular process. In one case was about $1 million, from $1 million to like $350,000. So dramatic lowering of resin costs, capital costs needed for that particular step. So very quickly, how do radial flow columns work? Well, the flow in these columns is introduced. So this is a picture, a cutaway of one such column. So the flow comes in through the center. And in larger columns, we don't have these spokes anymore. We have two impingement plates. So flow comes in, hits the impingement plate, that forces the flow direction to change to the outside. And just as it's going through these channels. And on the outside, just inside the outer wall of the column is a porous frit, which is a cylindrical frit. And then in the center of the column, again, there's a cylindrical frit. So instead of a circular frit on the top and a circular frit on the bottom, as happens with conventional columns, here you have two cylindrical frits. And the resin is packed as a slurry into the space through these packing ports. And so in bigger columns, you have more packing ports, but you have a manifold, and through the manifold, you simply, once you've primed your column and filled it with buffer and driven all the air out, you simply pump in your slurry, and the slurry packs up in this intermediate space, and all the excess buffer gets squeezed out through the top or through the bottom. And when the column is packed, no more resin will go in. If there's a pressure gauge at the inlet at the outlet of the pump, it'll rise and tell you when the packing pressure hits a certain compaction pressure. That's it, the pump is stopped, and then you can condition your bed by cleaning the lines, running the flow in the forward and then reverse direction a bunch of times, and check your HETP and asymmetry as you might any other column. So very convenient, and these things have been scaled up from little bench scale columns all the way to several hundred liters. And you can do that in one step. And of course, as you scale up to large scales with conventional columns, you have issues, right? You have issues that nobody tells you about, which is if you have a very thin bed and you have a 2-meter column, well, the flow has to, if this is 10 centimeters and the flow is going 1 meter in this direction, 10 centimeters down, and 1 meter in this direction, guess what? You're going to have flow going preferentially down the center as compared to the outside, so you'll have earlier breakthrough in the center than the outside. So your peak volumes, your capacities of the resin are not going to be as well utilized, your cleaning is not going to be as effective, and your capacity is going to be a little bit lower. Whereas in radial columns, the flow comes in, part of the flow goes through the top, and then the inside, the other part goes through the side, which is the same distance y, and then through the bed, distance x. So no matter which way the flow goes, you're always traversing the same distance, and therefore it's seeing the same back pressure. And so the flow profile and the elution profile are the same. And this is data from Genentech, project we did with them, where they essentially showed that with axial flow, this is a kilo run. This is not little bench scale 5 mil or 10 ml run. They did lots of work on little columns and scaled them up to kilo scales. And this is showing on a kilo scale that what used to take them 8 hours, they were able to do with conventional columns, they were able to do with radial flow in 2 hours. So it's saying if you want to save on cycle time, it's a very low cost, very effective way of being able to scale up and reduce cycle time. And they found that peak asymmetry, recovery, impurity clearance, and all that was unaffected. Okay? So here's the data showing that product recovery, monomer, HCP, and protein A, all the specs that they have, release criteria for that particular batch met, and the process throughput was increased by a factor of 4. So you're not talking about 10%, 20%, 30%, any sort of small significant improvement. This is a big improvement. You're talking about 400%. Okay, so it's a low-hanging fruit that people can definitely use to improve their process, especially if they're scaling up to a large scale. We have many companies who are even using radial flow columns for development purposes because they're behind the 8 ball. They have so much screening and development work to be done, and with just using an ACTA and their columns, let's say doing antibody process, if each step takes 4 hours, and they have lots of resins to screen, lots of processes to do, well, guess what? They're not, many times you have just a few ACTAs or something in people's labs, and their timelines are so extended But if they use radial flow columns, then they can cut down that timeline and get through their process development much faster. So here's an example at a well-known large biopharma company where they're using 250 ml columns for antibody separation. So everything that they're doing in the entire process uses radial flow columns, and these columns are running at 100 mils a minute. Titer was 4 grams a liter, load was 1.75 liters, recovery was 92%, and the entire separation was done in under an hour. Something that would take 4 hours, 3 hours, and done in an hour. And then this, of course, shows what we were talking about, where in a clinical production, where they would have normally used a 40-liter column, had a capex for that particular step of $450,000, used $500,000 worth of protein A for, let's say, phase 2 clinicals, where they would make, a few campaigns, and the material, then the systems just sit around because they have to wait for clinical data, and so that resin is essentially wasted, whereas they were able to move that to a radial flow column, which is 1/4 the size, and use only $125,000 worth of protein A. And of course, with a much smaller column and much smaller system, the capex was much less. So you can see it's a dramatic reduction in capital cost and making your process more efficient and reducing the footprint. These columns can, of course, be compared with membrane absorbers. You have the benefit of both worlds, where you have the speed of kind of membrane absorbers, but you have the capacity of conventional chromatography. And then these are bench scale systems. This is our bench scale single-use chromatography system. You can see that we have removed the outer skins, which are very, very easy to remove. So these are just stainless steel removable panels. And inside that are pinch valves and flow path tubing and sensors. And so the flow path is neatly laid out inside the machine and can be easily removed within 15 minutes. And we say here removable flow path takes less than 20 minutes. We've actually clocked people following our instruction doing it in 14.5 minutes. Okay? So very simple. The flow paths come pre-sterilized, so you install them, you go ahead and start running. Know that your flow path is sterile, and then when you want to move to the next product, you simply exchange it out. All the software is 21 CFR Part 11 compliant. This is a video.
Now.
So the first step is to remove the cables out of the way to the side, and then open the sterile pouch. So this pouch is not sterile here, but your flow path will be in a sterile pouch, which you cut open, and take the entire flow path, which is actually pre-assembled, out and lay it down in the center of the machine like this. So it's one giant contiguous flow path, completely pre-assembled, and all you have to do is lay this flow path out, on the valve manifold, which are the pinch valves, and the flow, and thread the tubing through the pumps and the flow cell and the various detectors. So that's what he's doing right now. He's got the 4 inlets for pump A that he's setting through, each of the channels on the pump A manifold. Okay, so the solenoids are at the bottom, and they have a pinch clamp that moves up, the plunger moves up, and it will pinch the tubing. Alright, so he set that, and now he's taking the pump tubing through the peristaltic pump, threading it through the peristaltic pump, and there the pump tubing is installed. And he's going to do exactly the same thing with the B pump and the B valves. Okay, so there he goes. Now each of those tubes is labeled. Each of those tubes is labeled so that you put it in the right channel, and the corresponding valve is also labeled, so you can't go wrong. And here he is threading the tubing through the pump. So the tubing is now installed through the pumps, and the next step is for him to take the tubing through the two flow meters that are in line. And so there's a flow meter tube that sits across from the mini ultrasonic flow sensor, and so he just put those tubes in the ultrasonic flow sensor, as you can see. And the next step is to install the pH sensor and the conductivity and the air sensor. So he's threading the tube. He just push the tube into the air sensor and is doing the installation for the, Danny, is that the pH or the conductivity sensor?
pH1.
That's the pH1, that's the pre-column pH sensor. So he just put that in the slot. Yeah, and the next one is the conductivity sensor that he attaches a bracket to. And then he's sliding it into its slot, which is pre-labeled. There. So the pre-column conductivity sensor is installed. So we now have the tubing being installed for that goes to the column, that goes to the air eject valve, and that goes for the pre-column device, which might be a filter or a bubble trap or anything like that. And so the valves in the front that you see he's installing the tubing go to each of those ports. So again, these are pre-assembled, pre-labeled. So essentially lay them down on the individual channels that you have right in front of you. Okay? And the ones on the right are the ones going to the column, and the ones on the left are the ones going to the filter. Okay, and this one is the air eject tubing. So now what's left is post column. We are going to install the UV flow cell and the pH flow cell. So the UV flow cell just slides into the slot in the UV detector, and the pH flow cell is right below that. And the tubing, and so the flow goes down from the pH flow into the pH flow cell, comes up through the UV sensor and into the conductivity sensor, which he's putting a clip on now. So there he installs the clip.
Oh.
There the clip is installed, and then he just sets it down on the bracket, which is below, so it snaps in. There. And then these are the fraction, this is the fraction valve. So in this machine there are 4 fraction valves, and so he lays the tubing down over the fraction valves. Right? So the entire flow path is now installed, and so he's going to make the electrical connections next. The electrical connections for the pressure sensor, for the temperature sensor, and so forth. So that's the next step. Go ahead. That's the
Pressure 1.
pressure 1.
So there's the pressure sensor in the flow path, and he just made the connection of the cable to the pressure sensor. And that is the conductivity detector. So he's making the connection to the cable that goes into the instrument. And here is another conductivity detector, and he's doing the same thing. So there's a cable that goes into the machine, and he just connected the conductivity detector to that.
Pressure tube.
And that is the pressure tube. And so he's connecting, again, snapping in the pressure cable. And that is a temperature sensor, which is there in the flow cell, in the flow path. So he just connected that. He's next going to install the pH probes in the pH flow cell. So the pH probes are shipped separately because they have to stay wet. And so there he's screwing in the pH reference and sample probes, and then their connector is in turn connected to the cable that goes into the machine. And then he's doing the same thing with the pH sensor, which is post column. So the first one was pre-column, and this one, these are the pH sensors that are post column. So you simply screw in the sample and the two probes, and there now he's putting in the cable that actually goes into the machine. Right? And closes the cover and installs the lid on the flow cell. And the last step is to install the plates, the backing plates for all the pinch valves. So these are just bars with pinch. It's a pinch bar that goes over each of the tubing manifolds, and so he's now doing the installation for the pinch bar for pump manifold B. You simply install the bar and hand tighten the screws, and then similarly go ahead and install the pinch bars for each of the column manifolds. There's a column, which means to the column, from the column, to the filter, from the filter, the air eject, and so there are two sets of pinch bars that you install, which is what he's doing. Again, you hand tighten them, and then you install the pinch bar for the traction valves. Again, very simple procedure. It doesn't require the use of tools or anything like that. An ordinary lab scientist should be able to do the installation. And then the next step is to put the plates on top of the flow sensors. So remember, we had put the flow sensor tubes, we had snapped those in, and so now on the ultrasonic flow sensor we are putting the plates that go on top. So that's a flow sensor for one pump, and this is the flow sensor plate for the second for the second flow meter. And you can lightly tighten those with a screwdriver, which is what he's doing right now, so that they remain in position and don't move out, because you want the flow accuracy on these flow meters is astounding. It's about 0.1%. So, and can go down to very low levels in terms of flow rate, so the flow range is excellent. So there he now screws in the last couple of screws on the flow meter plate. That's it. The flow meter, the whole flow path is, the installation is now complete. And for running it, you can simply lower the top hood and slide in the sliding panels that are on each of the three sides. So you can see it's very simple to install, and the disassembly the disassembly or uninstallation is just the opposite of what we just did.
And then, of course, we have larger systems going up to 10 liters a minute. There's our screenshot of our software, very simple. Manual runs can be done simply by clicking on these valves. So you can click on any valve and the flow will go through those valves into the column, and then either forward or bypass or reverse through a pre-column device if you want to put a pre-column filter, for instance. Similarly, we have buffer dilution systems, where in this one, for instance, you may have concentrated buffers, a Wi-Fi pump, and so this could be 5x, 10x concentrates, which get diluted inline, where there's an inline mixer. You can also have pH and conductivity feedback that can alter the speed of the pumps. And if the buffer concentration, conductivity, or pH is outside the range, then the buffer exits, otherwise it goes through the flow. This just shows that the dilution process is very, very stable, and that you don't have a lot of fluctuations. And with a transition time now between different buffers, we are down to 22 seconds, where we can get a stable dilution from a constant. Then these are latest dual column capture system, continuous capture systems, and inline buffer blending. And so this can take a clarified harvest from a feed supernatant and is loaded on, alternatively, on two columns. So while one column is loading, then the other can be washing and eluting. And then once that column is finished loading, then that column goes into the non-load or wash, elution, resin, equilibration mode, whereas the second column goes into the load. So all these systems come with, also pre-column filters, pre-column sensors, post-column sensors like UV, conductivity, pH to monitor, the process just like you would on any batch system, except now you're doing it continuously from, let's say, a perfusion bioreactor going through either an ATF continuous centrifuge onto, a balance tank and into the column. The exciting thing about this is not only can we do it continuously, but we have enabled the ability to provide the ability to make buffers on demand. So by just putting in 4 stock solutions, the mono the acidic component of a buffer, concentrated acidic component of a buffer, and the basic component of buffer. Now by blending those two in any ratio, you can get any desired pH. And then adding salt solution, now you can get that buffer at the right pH with the right conductivity, and then you have water, you can have it at the right dilution or the right molarity. So we control all four aspects: pH, the blend ratio, the pH, the conductivity, and the dilution, and we're able to make buffer on demand. And this can be any kind of buffer. And so this is the first system of its kind that integrates continuous chromatography with inline buffer blending. And so this is a capture system. So in antibody production, you have a capture system, which is, as we described earlier, you go through protein A capture. And then once you go through the protein A capture and harvest and load your harvest and you elute your antibody, then it goes into a viral inactivation step, which is a low pH hold. And then after that, typically goes through a series of flow-through steps: ion exchange to remove any residual DNA, HIC or CEX chromatography to remove any HCP, host cell protein, and then of course through nanofiltration to remove any of the salts. So what did we do? Of course, this is still the continuous capture system, of course, with the whole software displayed, with the column 1 and the column 2. But then we also made a second system. We're providing a second system which integrates the ion exchange column, the hydrophobic interaction column, and the nanofiltration. All those three aspects are on one skid. And how do we do that? So the captured MAB and the virally inactivated solution or antibody is pH adjusted in this skid and passed through the ion exchange column. And then in line we have salt adjustment so that it can go through the HIC column and is passed through the HIC column, and then the salt is removed by nanofiltration. So all those three continuous flow-through operations are done in this skid. So we provide the ability to be able to do the entire process with just antibody production process with just two skids. So you can see something that would normally take a huge plant can be done in a room which is about 10 by 20, 10 feet by 20 feet. And so we have very powerful tools, whether it's radial flow chromatography that enable several times the flow rate with small footprint, pre-packed columns, fully automated, customizable chromatography systems with small footprints, single-use chromatography systems, inline buffer making or buffer dilution systems, and then continuous downstream processing. And if you all are interested, anyone is interested, suddenly ping us, send us an email, and we'd love to have a one-on-one discussion with you on any of these solutions that can augment your process and help your process scale up faster, get to market faster, and reduce cost of manufacturing and cost of scale up. Thank you very much. Any questions? Okay, so this is from Arjun. Arjun, good question. So this is very, very simple. So the way to convert any process, to scale up any process, is to convert linear flow rate into bed volumes per minute, meaning residence time. So in any ion exchange separation, any affinity separation, all the scale up is based on contact time, right? So let's say you have, you're going through a column with, with let's say a 10 centimeter bed, and you're going at 100 centimeters per hour. Okay. Yeah. So that might be like 6 CV per hour. Okay. So your residence time is about 10 minutes. If that's the case, then you scale up with that same residence time in the radial column. So if you calculated your residence time with your particular process, and let's say your residence time is 2 minutes, then you do the same thing. So you take, let's say, a 5-liter column, radial flow column, and you would run it at 2.5 liters a minute, because 5 divided by 2.5 would give you a residence time of 2 minutes, right? Typically what happens is people are running very, very slowly in terms of bed volumes per minute in conventional columns. And what we tell people is, look, that's your baseline. Start with that, because we don't know what the capacity is of that particular resin. So with respect to flow rate, so start with that baseline. And so, with the summary that we showed you of the Genentech presentation, they didn't just arrive magically at 4 times. They started with the baseline process and they converted that to bed volumes per minute. Okay, so if it was, we just say, okay, you have a 50 mil column, you're running it at 10 mils per minute, so you're running 0.2 bed volumes per minute, right? So run your radial flow column, whatever it is, at 0.2 bed volumes a minute, use that as a baseline, then run it at 0.3 bed volume a minute, 0.4, 0.5, 0.6, and at some point in time, either you're going to be pressure limited, which most of the time you're not with common resins, or you're going to start to see a small drop off in capacity. So if you're getting 5 times or 6 times the flow rate, and even if you get 5% reduction in capacity, that's fine. You can just have a column which is 5% bigger. So make up for that difference, but now you've gained about 4 or 5 times the speed. So that's the calculation, that's the work that we did with the folks at Genentech and other folks do as they scale up on radial flow columns. Okay, thank you.